In this video, we're going to be looking at correlation. And the correlation coefficient, you recall, is a number that tells us something about the strength and the direction of a linear relationship. Now, if it's a perfect linear relationship, the R is going to be either positive 1 or negative 1. A perfect positive linear relationship. In other words, every point in your scattergram actually falls on the same line. That's what we mean by perfect linear relationship. If it's in the positive direction, R will be positive 1. If it's in the negative direction, R will be negative 1. And those are your two endpoints for what you can have for R. Every other R value that we could have will be between negative 1 and positive 1. If there's no linear relationship, or if the line is a horizontal line, then R is 0. In order to look at a correlation coefficient, in order to calculate one, both variables have to be quantitative. And R has no units. It doesn't change when the measurement units are changed. So here are some examples. In this first one, so we'll call this one up here number 1. In number 1, correlation for that when it was calculated is 0. There's no linear relationship there whatsoever. Here in number 2, there's a slight downward relationship. Slight. That's why it's negative 0.03. It's not strong. The closer you get to either negative 1 or positive 1, the stronger that correlation is. Number 3 down here, we're getting stronger, and this time we're in the positive direction. Correlation here is 0.5. Number 4 here, we're getting even stronger. That's a 4. Getting even stronger, and this is in the negative direction, negative 0.7. And look how strong we're getting now in number 5. 0.9. That's a very strong relationship. And here we have negative 0.99 in number 6. That's about as strong as you can get without them all lying on the same line. Some examples, if you do a study and look at these things. Husbands versus wife's ages. The correlation coefficient on that one is 0.94, so that's a pretty strong linear relationship. But when you look at heights, you only get 0.36. It's a much weaker relationship, but it's still in the positive direction. And golfers' putting success. Distance of putt versus percent success. It falls in a very linear relationship. It's a very strong relationship, and it's in the negative direction. Okay, but let's look at this. Not all relationships are actually linear. If you calculate the correlation for this, you get a correlation of negative 0.06. That is extremely close to 0. And remember, 0 indicates either a horizontal line or not a linear relationship. So you would look at that and say, is there any linear relationship there? No, there isn't. It's actually a curved relationship. So correlation, when you don't have a linear relationship, the correlation is going to be misleading. So you want to do a scatter plot first to make sure that there is some kind of linear relationship and not a different form of relationship going on. And here are some problems that we have with correlations. Outliers can really inflate or deflate the correlation, and we'll show that on the next slide. So we really have to be careful with outliers and look at if we can take them out, if we can have the grounds for taking them out. And if you combine groups inappropriately, you may mask relationships, like a third variable. It may not show the relationship that's there. And you may see something very different when you separate the groups. An example would be putting a whole population together and trying to look at a correlation with another variable, as opposed to breaking it out by male and female and seeing that maybe there's a strong correlation with the males, but no strong correlation with the females. So here are our outliers. So this outlier in A, we're going to look at A first, that outlier decreases the correlation because if you look, let's do another color here. If you look, there's a pretty good linear relationship there, and it's in the positive direction. And this outlier is so far out of the pattern that it actually decreases the correlation that you have there. But then if we look over here at B, what we have without the outlier up there is it's a linear relationship, but it's not as strong as it is when we add that outlier up there, because that kind of pulls it to a specific line, and it has the effect of making it feel like there's that strong a relationship down in this part. Now, if there was this much data clumped like this the whole way along up to the outlier, we really would have that strong correlation. But the outlier is just making it look that way by increasing that correlation that exists. Okay, so what is the correlation coefficient? How do you calculate it? Well, here is the crazy formula for it. So, we look at two variables, x and y, and we have n individuals that we're looking at. Okay, so we have x sub 1, these should be subs, so it should be x sub 1, all the way up to x sub n. Okay, and that's just saying the first value, the second value, the third value. And then we have the corresponding y values from our ordered pairs. Now each variable x and y is going to have a mean and a standard deviation that we can calculate. We've already learned how to calculate the mean and the standard deviation for a variable. So x bar in this formula, that's the mean of x's, y bar is the mean of y's. S sub x is the standard deviation of the x's, and S sub y is the standard deviation of the y's. And what we're going to do is we're going to look at the deviation between each x value and the mean divided by the standard deviation. We're basically standardizing the deviations from the mean for both variables and then multiplying them together. You add all those up, divide by n minus 1, and you get the correlation. So let's look at an example of how that. So we're going to look at per capita gross domestic product and average life expectancy for countries in Western Europe. So for each country, you see, and there are 1, 2, 3, 4, 5, 6, 7, 8. There are 10 countries here. For each country, we're given a per capita GDP, which is the X value, and a life expectancy of people there, which is a Y value. And we're going to see how strong of a linear relationship that we have by calculating the correlation. So here's what over here. We've lined up our X's and our Y's. This right here is X minus X bar. And this is Y minus Y bar. Each of them then divided by, this is divided by S. Let's get that right. It's divided by S sub X divided by S sub Y. So this here is X bar, this is Y bar, this is S sub X, and this is S sub Y. Don't know why all those things didn't come through together. And then this column is this times this. So it's multiplying those standardized deviations together. So that whole big sum part, the summation part in the formula for ours comes to 7.285. So again, this part was the last column, and when we added them all up, we got 7.285. Divide that by 9, because our n was 10. 10 minus 1 is 9. And we get an R of 0.81. So now let's ask ourselves, what is the strength and what is the direction of this linear relationship? It's in the positive direction, so it's going up. As GDP goes up, so does life expectancy. And it's pretty strong. 0.81 is getting to be pretty strong. So we have a fairly strong relationship in the positive direction.